All right. Hello, everyone. So you want to ask about the poker problem. Let's pull that poker problem up from the homework. So, yeah, let's talk about it. So let's not do that problem per se. Let's do a different problem. But we'll make it almost identical. So I guess the question should just be for, this is number 4 on the homework, but it's modified. Oh man, the pen is working nice today. The answer to your question, do you need to choose the category before you choose how many from that category, is it doesn't really matter because it's all going to be multiplied together in the end. And multiplication, as it turns out, is commutative, so it really doesn't matter. And then, yeah, we'll go over what a combinatorial argument is. So, yeah, okay. Maybe I'll even go over number 2A in the homework. I don't know. Maybe I'll do something different. We'll see. Okay, so let's pick how many... Or really, I want to ask, how many ways can we get two pairs in a 5-card stud? So, okay, let us begin to attack this problem by dealing with what kind of choices we have to make. So what does two pairs mean? 2 pairs means that we get, say, a 2, a king, and then say a different card, so a 5, right? So what are the choices that we have to make? So the first choices that we have to make are what type are the pairs, right? So there's one pair and there's another pair. So we have to choose 2 different types for the pairs. And so what we're going to do is, sorry, I was just reading that question. I think the answer to your question is you definitely need a C3 one and a C4 one in that answer. So, yeah. Okay, and then you have to pick the other card. And so, then we have to pick 2 out of the 4 suits for this pair, 2 out of 4 suits for this pair, and 1 out of 4 for this pair, or for this card. So we need to pick 2 different types of cards that are both going to give us pairs. So the way to pick out of 13 types of cards, we'll pick 2 of them. And then we have to pick 2 out of the 4 suits. And then we have to pick another 2 suits out of 4 suits. So this here is choosing the 2 types of pair. and then it's choosing the suits for each pair. But we're not done yet, because we still have to pick this last card. So how do we pick the last card? What we do is we say to ourselves, okay, we need to pick out of the 11 remaining, we need to choose one. And then we need to do for choose one for the suit. All right. So this would be the answer to this question. Now, of course, you might say, and I've seen some questions like, do we have to write out all of this, or can we just not just leave it in this form? The answer is you can just leave it in this form. If you really want to write it out, you can write this as 13 times 12 divided by 2 times 6 times 6 times 11 times 4. And so you can kind of compute this. How come the second pair isn't 12 choose 2? So here we have picked two types of card. So because we picked two types of card, we've picked the 2 and we've picked the king, right? That's what happens in this 13 choose 2. It gives us this card and it gives us this type of card. This is going to pick the suit here. So if this is, say, spades, and this is diamonds, this is, say, hearts, and this is diamonds again, and then this is, say, clubs. So we're eliminating two types of card here. So the point is that we have 13 minus 2 left. And so we're excluding 4 of a kinds. So no 4 of a kinds. And no full house. So we're okay. And then the other question you guys had was, what is a combinatorial argument? And so maybe in order to answer that, I will do an example problem. Let's think of a good one. Well, let's try to prove this. So what we want to say is that there's the same number of ways to choose. So what does this symbol mean? This symbol is n choose k. So it means if you have a bag of n items and want k of them, there are n choose k ways to pick that collection. And it's a collection in the sense that order doesn't matter, right? So it doesn't matter if you pick the elements in one order or another order. What you do is you pick k elements out of a bag and you throw them into another bag and you jumble them up again. So you don't really care what order they're picked out in. So what does this symbol mean, right? So this symbol means if you have a bag of n objects and you want n minus k of them, the number of ways, so n choose n minus k is the number of ways to select these elements. So the combinatorial argument that proves this, so this can actually be proved algebraically. You can write this out as n factorial over k factorial, n minus k factorial, and then you'll see that this is equal to n factorial over n minus k factorial, and then here what we're going to get is technically n minus k factorial, and you'll have to simplify this term. When you do, the n's are going to cancel. You're just going to get a minus of a minus k, so you're going to get a k factorial. So you see that these two terms are equal. So this algebraic proof is actually easier than the combinatorial proof, I would say, at least in terms of length. But the combinatorial proof basically says if you have a bag of n items and want k of them, there's n choose k ways to do that. If you have a bag of n objects and want n choose n or n minus k of them, there's n choose n minus k ways to do that. So as it turns out, what you're really doing here is in this symbol, you're taking n objects in a bag, and you're either putting them into a group of k objects or a group of n minus k objects, which are the rejects. But as it turns out, that's really the same thing as taking a bag of n objects and putting n minus k rejects into the first bag and then selecting the k things that you want. Right? So either you can want the n minus k things or you can want the k things, but in the end, it's the same process, right? Because the same two bags are formed. You can kind of switch these two up. You can say, well, either I pick k things and I leave out n minus k in the original bag, or I pick out n minus k things and I'm left with k things in the original bag. Either way, you're going to get the same selections. So this is the combinatorial argument, is basically this part here that says, this is the n choose k way, this is n choose n minus k, and they're the same because in the end the same two groups of objects result. Okay, so let's do one more combinatorial argument. Let's do something a little more complex. Let's try to show this fact. So as it turns out, when you add up all of the n choose k's from k is equal to 0 to n, you're going to get 2 to the n. Now, there's another way to do this using the binomial theorem, but let's do this using a combinatorial argument. And so the combinatorial argument is going to basically be like this. 2 to the n is the number of ways to, if you have n objects, so if you have n objects, there are 2 to the n ways to either select or not select, right? This is equivalent to saying that there's 2 to the n ways to say that this light switch is on, this one is off, this one is on, off, on, say what this one is off, right? So there are 2 to the n ways to do that. Well, okay, let's imagine that we are specifically going to ask how many ways can we select exactly k objects, right? And turn them on, or make a check mark on them. And so the answer to that is n choose k. But what we realize is all the different ways to switch the lights on and off, they all get grouped. They can all be grouped by the number of objects that are turned on. So we can group all the ways to turn n light switches on or off by the number of switches that are on. And so given the fact that there's going to be somewhere in the range of 0, 1, 2, all the way up to n ways, that means that either we're going to have 0 light switches on, or 1 light switch on, or 2, or 3, or n. Therefore, n choose 0 plus n choose 1 plus n choose 2 plus n choose n is 2 to the n. Now this is a combinatorial argument, so the thing is that it doesn't feel very precise sometimes. But it was asked whether or not there was a way to prove this algebraically, and there is. The way to prove this algebraically, the simplest way, is the binomial theorem. Which says this, right? It says that x plus y, whoops, I don't want that summation yet. Is equal to the sum of n choose k, x to the k, y to the n minus k equals 0 to n. So if you believe in the binomial theorem, and we can prove the binomial theorem in different ways, actually I think you could probably prove it by induction. Well, that didn't spell induction at all. Let's try again. But we're not going to do that proof, right? We're not crazy enough to start on that. Actually, no, we could do it. You guys have the tools to do it. You know, you have the gear. Whether or not you realize you have the tools yet, you do have the tools to do it. I think it's a little bit of a mature proof. Is it hard? No, it requires your homework problem, actually. It requires the homework problem that says that n choose k plus n choose k minus 1 is equal to n plus 1 choose k. If you believe in the homework fact, that is the thing that you need for the induction. Anyway, but we don't care about proving the binomial theorem. We're going to use it. And so what we want to show is that 2 to the n is equal to the sum of k equals 0 to n of n choose k, x to the k, y to the n minus k. So actually this proof is pretty easy. Well, I shouldn't say that, but I'm going to say it. This proof is pretty easy. And the reason why this is doable is if you set x equals to y equals to 1, right? Well, so your answer on the homework needs to be like consider the number of ways to do this thing. And then you want to say, okay, in that case, so I'll give you a hint for the homework problem in just a second. But let's finish this proof first. This proof is easy. So if you set x equal to y equal to 1, then we see here that 1 plus 1, I'm fairly convinced, is 2. And in this case, we would get n choose k, 1 to the k, 1 to the n minus k. As it turns out, this is always just 1. And so we can drop those ones and just get this term. So this is the algebraic proof. So which is better, the combinatorial or the algebraic? I feel like the algebraic definitely seems more rigorous. If the combinatorial proof was written out correctly, I think it would be equally rigorous. But anyway, so I think the hint. So what you want to show in the homework is n choose k plus n choose k minus 1 is equal to n plus 1 choose k. So my hint to you is this. You have a bag of n plus 1 things. So we're going to number them 1 up to n plus 1. Now, you have two choices. And this is the hint that gets you 95% of the way there. One, you pick the item marked n plus 1. 2, don't pick that one. Oops. Theoretically, this class is devoted to the inclusion-exclusion principle, which we'll get to, but I don't mind doing some homework review. So if you do pick it, then the questions that you have to ask are, how much is left in the bag? Okay, that's how much is left in the bag. The pen is kind of fighting me a little bit sometimes. And the second question is, how many do you still need to choose? And so, and you have to do these two questions for both of these. So you do it for this one, and you'll also do it for this one. And so if you do that, that's the combinatorial argument. Basically, you say you start with a bag of n plus 1 things, you number them, you either pick the thing numbered as n plus 1, or you don't pick the thing numbered n plus 1, right? If you do pick the thing marked n plus 1, then how much is left in the bag and how many do you still need to choose? If you don't pick the thing marked n plus 1, how much is still left in the bag and how many do you still need to choose? And then you can basically add those two conditions. So, I mean, the hint is that the equation is the thing right here. So, you know, the hint is the problem now. Okay, cool. So I think that's all that I want to say about that for now. Oh, right, the other thing to say, I hope that all of you got an email, right, from the Discord office hours, and hopefully you've seen it and you're getting on Discord and that kind of stuff. If you have any trouble getting on Discord, you can send me an email, but I will say I'm not tech support, but I will try to help you. Okay. So let's talk about the inclusion-exclusion principle, right? So the formula that I'm going to give right here, this formula here, sometimes you'll hear this called like the double union formula. The reason why this is called the double union formula is because, well, it involves two sets and we're unioning them. But really what it's doing is it's counting the number of things in each set. So for instance, if we mark this set as A, we mark this set as B, this is A intersection B. So if we want to know how many things are in A, and I should say that the absolute value bars in this case are, like if I say the absolute value of X is the number of elements in the set X. So, if we consider, let's just do a small example now. Let's say that the number of things in A is 15. The number of things in B is 13. And the number of things in A intersection B is 4. Very good. And so, the thing about it is, this Venn diagram is not how we're usually going to draw Venn diagrams. I should just say, maybe I'll just write it out here. Like, I'll just write it out. The number of things in A is 15. The number of things in B is 13. The number of things in A intersection B is 4. So why is the number of things in A union B equal to the number of things in A plus B minus A intersection B? And the answer is because 4 of these items are in A, right? But they're also in B. So how many things are just in B? So things that are in, what I mean by just in B is B intersection A complement, essentially. Yeah, exactly. So we don't want repetitions. And so because there are 13 things in B, but we know that there's 13 minus 4 unique things. So there's 9 things that are in B, but not in A, right? And similarly here, there's 15 minus 4 things that are in A, but not in B, right? So this is the number of unique things. This is the number of unique things, and 4 is the number of things uniquely in A intersection B. Therefore, we can use this formula, but if we use the formula just with the original numbers, what we see is, so we can add up these numbers. So we can say 11 plus 9 plus 4, and that's definitely the right answer, right? So that's going to be the right answer. But let's say that we didn't actually calculate those numbers. What if we just stuck with the original 15, 13, and 4? What we're going to get is the number of things in A union B is equal to 15, right? The number of things in A plus 13 minus 4. And so is that going to be equal to the same thing? So this is 24. And this is what? This is 28 minus 4. And so the way that the formula works is that it allows you to double count. So it says, okay, count up everything in A, count up everything in B, and then subtract off one copy of the intersection, because that one copy of the intersection is going to be the number of times that the intersection is going to be one copy of our double counting. So we've counted these 4 people or these 4 objects in A, we've counted these 4 objects in B, and now we have to subtract off one of our instances of the counting. And so that's where the double union formula comes in. Okay. So let's apply the double union formula to a silly question. So there are 81 people in this class. Not quite that many on the stream right now. Those who missed the stream are missing out. So let's say that 43 people in the set like YouTube, and 63%, I keep saying percent, 67 people like Discord. So this is just absolute, the number of people, not percentages. I made this example through an absolute random guessing of a survey. I'd never asked a single person. So, okay, but how many people must like both? So there's 81 people in the class. So assume that everyone likes one thing or the other thing. I keep drawing through it. I assume everyone likes one thing or the other. Right? So what are we going to... is 27 the answer? Let's see. So 81 is going to be equal to what? It's going to be equal to the thing about, let's say, YouTube, which we'll denote as Y, union Discord. Right? So it's the union, not the intersection. And so then we know that the people who like YouTube is 43. The people who like Discord is 67. And now we have to do a little bit of... yes. Now we have to do a little bit of subtraction. So what we have to do is we have to say the Y union D, the number of things in Y union D, is equal to the number of things in Y plus the number of things in D plus, or I'm sorry, not plus, obviously not plus because it's inclusion and exclusion, minus the number of things in Y intersection D. And so we can basically solve this by doing this. We can say 81 is equal to 43 plus 67 minus, you can either leave it in this form or you can even just replace it with a variable, call it x. So let's calculate. So what is 43 plus 67? 43 plus 67 is 110. So 81 minus 110 is equal to... Okay. So what I get here, this is 110, this is 81. So what we're going to get here is that technically minus 29 is equal to negative x, right? I don't feel like writing it again. So you kill off the negative signs. And so now you've got it. All right. So this next part of the question is just a little modification of the question. It's not really an inclusion exclusion problem per se. They got 27 because they looked at the number of people on the stream currently. Oh, is 15 too many? All right, let's change that number. 8. We're downgrading the number of people who don't like things. So if 8 people don't like either, I have mixed feelings about YouTube and Discord, but it does seem like both of them are working out in our case, so let's not be too negative about it. So anyway, yeah, if 8 people don't like either, then the actual number of people, so this is like the number of people in, say, the universe, and I'm using n of u to also indicate the magnitude or the cardinality or whatever of a set. So what we have to do in order to figure out the number of people in the set of people who like YouTube and Discord, I keep doing that. Let's undo that. is going to be 81 minus 8, right? So 81 minus 8 is 73. Cool. And so if we do it now, we'll see if this number even works out. So we'll say that it's equal to what? 43 plus 67 minus x. And so this is still 110 because I haven't changed this. And so 110 minus 73 is 37. Good. Okay, so what we're going to get, if we subtract 73 over here, I'm going to do the algebra differently this time. We're going to get 0 is equal to 37 minus x. And now that 0 is equal to 37 minus x, we just know that x is equal to 37 in this case. All right. Fun times, right? So let's move on. Do something a little more interesting. So here is the three-set union formula. So you see that actually the three-set union formula is very similar to the two-set union formula, except it has some extra terms. So basically, let's prove the three-set union formula. I like the proof because it's simple. So if we want to know the things in A union B union C, what we can do is we just add up the number of things in A. So when I draw a tick mark or a hash mark on every set, what I mean is I'm adding up the things in that set once. So for instance here, I'm adding up the things here once, once, and once. So that is this thing, the number of things in A. Now let's do the number of things in B. So you add this thing, plus this thing, plus this thing, plus that thing. Right, so now we see here the double union formula essentially, right? Because we have these two regions here which are double counted. And that's the reason why eventually we're going to have to subtract off an A intersection B, but we'll get to that in just a second. Now let's look at C. So C gets this, this, and that. So what do we see? What we see is that we've counted the just A parts once, which is fine, the just B parts once, which is fine, and the just C parts once, which is also fine. But we've counted all of these other parts, we've double counted. And then we've triple counted this thing. So that's even worse than double counting. So let's look at this set. So A minus A intersection B. So we get rid of one copy of that. So let's change our color. So we are going to subtract off one copy of A intersection B. And let me just put a green here. Then we're going to subtract off one copy of A intersection C. So A intersection C will cancel out this one, and it's the middle one here. And then finally, blue. We need to cancel out everything from B intersection C. So we'll cancel out one of these. Just one. The other one stays. And unfortunately, if you notice, we canceled this one too. So all three are canceled. So what do we have to do? Well, the formula basically tells us. we have to add on one copy again. So this is the triple union formula, right? And you should believe the triple union formula mainly because it's the formula that kind of does the thing that needs to be done. It continues, it just adds on all the singleton copies, it subtracts off all the doubles, and it adds on the triple. This proof is testable. I would say. Maybe I'll put quotation marks around testable. Okay. So, all right. So this isn't the Venn diagram of this situation. This is just the proof of the formula in general. So now let's just compute this thing. So what is A union B union C? Well, that's going to be equal to 23 plus 32 plus 15 minus, and then you see A intersection B, so 12 minus 5 minus 4 plus the triple union plus 2. So now we'll pull out a calculator and just do this thing. So we'll say 23 plus 32 plus 15 minus 12 minus 9, I guess, plus 2. So in total, $51. Okay. So if I tell you to draw a Venn diagram of this situation, let's actually show what I mean by a proper Venn diagram of this situation. Oops, that's kind of, it's outside of the universe. Has anyone seen the Color Out of Space movie? Do you have to memorize the formula? I would say yes and no. You should understand that you're adding the singletons, subtracting the doubles, and adding the triple, right? So it's one of those, it's way better to understand the formula than it is to memorize it exactly. But, I mean, I guess you can call that memorization. I'm not sure whether I'll make you memorize the triple union formula. Probably not. Let's say no. Don't memorize this. Okay. So what I'm going to do is I'm going to put 2 in this thing. So that shouldn't be terribly surprising because 2 is A intersection B intersection C. But what I am going to do is I'm going to say, okay, well, let's take A intersection C first. Whatever. Yeah, that's fine. A intersection C has 5 things in it, but I already have 2 sitting in here. So what I'm going to do is I'm going to write 3 in this set. And the reason why I'm going to do that is because I want these 2 things. Now, this is A intersection C when you add these two, this part here and this part here. When you add this part here together, this is A intersection C. So I want these 2 numbers to add up to 5. All right, let's do the same thing for B intersection C, which I forgot to do. B intersection C is 4. So 4 minus 2 is 2, right? So this 2 is a 4 minus 2. Now let's pick a different color, purple. A intersection B is 12. So if A intersection B is 12, then this is 10, right? Because there's 10 things left. Okay. So now let's deal with A. I guess A can be green. All right, so the point is that we have 23 things in A, but we've already accounted for 10 of them, 2 of them, and 3 of them. So we want to subtract off 10, 2, and 3. And I think when we do that, we are going to get, 8 left. Then I can use blue for this thing. And so if I ask a question like, okay, so let's say 32 things in here, minus 3, oh no, I'm sorry, minus 10, minus 2, minus 2. And so what we're going to get is 22, 20, 18. So we'll have 18 things in here. And finally, we'll do this in purple. So C had 15 things in it. 15 things minus 3, minus 2, minus 2 is 8. Okay. So you could ask the question, why would we ever want to do this? And the answer is because I can then ask you a bunch of different questions. I can say, for instance, how many elements are in, say, exactly one set? Let's see, how many elements are in exactly So that's a decent question. And if you were trying to use these formulas, it's actually very difficult to kind of arrange these formulas correctly in order to get those answers. But given this Venn diagram, you see that there's 8 things that are in A but aren't in any of the intersections, 18 things in B that aren't in any of the intersections, and 8 things in C that aren't in any of the intersections. So the answer is just 8 plus 18. Yeah, there's exactly 8 elements in A that are, I shouldn't say that. There are 23 elements total in A. There are 8 elements that are in A, but not in anything else, right? So when I say uniquely in A or just in A, that's what I mean by that. And then same thing with B. There's 18 elements that are just in B, but not in any of the other sets. 8 elements that are in C, but not in any of those sets. So I can ask you a bunch of different questions like that. I can say, well, how many elements are in exactly 2 of the sets, right? If I say exactly 2, well, then the answer would just be 10 plus 3 plus 2, which is hopefully 15. And again, this is actually something that's kind of difficult to compute just from the triple union formula. The triple union formula is extremely useful, but it doesn't always give you every single element of every single set. So this is definitely a way to do it. If I wanted to ask you questions like, how many elements are in A, but not in B, right? You can answer that question pretty easily. If I say how many things are in A, but not in B, and remember that but is the same thing as intersection is the same thing as and. So the things in A intersection B complement, so the things that are in A but not in B, are 8 plus 3, right? That's right, 11. So it's actually kind of easy given this process, right, to generate many answers to various different questions about Venn diagrams. So I think this is kind of the reason why you want to do it. Now, what is the algorithm here? What's the algorithm that I used is you always start, right? You start in the middle with the triple intersection. And so you start with the triple. And then you calculate the double intersections. Then you calculate the singleton sets. And then you will calculate if I give you a number. So if I say there are 60 total things, right? If I say that the number of things in the universe is equal to 60, but we know that the number of things in A, B, and C, when you add them all together, is 51, then there should be 9 things out here. And that's assuming this, right? So I just made that up. But the point is that if you're given enough information, calculate the complement. So that's basically the process with these questions. I know that I did some crazy stuff in the previous lecture, so I figured I'd take it easy on this one. Okay, let's do one last question about this stuff. So if we have A union B union C is equal to 83, the only purpose of this question is to show you two things. One is that, and let's say that the number of things in the universe is equal to 100. And we'll just keep that number aside for a second. So we know that we can calculate the number of things in A union B union C is equal to the number of things in A plus the number of things in B plus the number of things in C minus A intersection B minus A intersection C minus B intersection C. And then I ran out of room, but I'll add it on here. Okay. So we know the formula. And so now we can apply it. So let's do that. So we substitute here. We have 83 is equal to 62 plus 55 plus 31 minus 23 minus, but then you see here I haven't included A intersection C, so I'm just going to substitute an X in there. Subtract 16 and then add on the 2. I don't know, both of my examples I have A intersection B intersection C as 2, but of course you can say, well, that's not guaranteed, and you're right, it's not guaranteed. So what do you have to do to solve for X, right? Combine terms, right? So we just add up all the positive numbers. Let's see about those positive numbers. 62 plus 55 plus 31. So this is 148. So plus another 2 from this. So this is 150. Oops, 50. And then we subtract off 23 minus 16. So let's see, 150 minus 23 minus 16 is equal to 111. So 83 is going to be equal to 111 minus x. So we can do one of these standard algebraic tricks where we flip them, right? We subtract both things off both sides. So we say x is equal to 111 minus 83, which is 28. So therefore we know that A intersection C is 28. All right. Cool. So let's draw the Venn diagram of the situation. Whoops. Left the universe again. Okay, so where do we start? We always start, step one, you say the triple, right? The triple intersection is 2. There we go. Now let's make the B intersection C purple for no reason. So if B intersection C is purple, this is 16 minus 2, so 14. Let's make A intersection C green. So this is 26, right? Because we have to subtract off 2. And let's make this one blue and hope that I have enough space for it. So 23 minus 2 is 21. There we go. So now, how many things are in A? So we know that there's 62 things in A. So if there's 62 things in A, but we've already accounted for 21 of them, 2 of them, and 26 of them, then what are we going to end up with? We're going to end up with 13 that are just in there. Same thing with, let's do B now. If there are 55 things in B, and we have to subtract off 21, 2, and 14, what are we going to get? We're going to get, well, whatever it is. I don't trust my mental math anymore. Oh, is that actually a problem? I think it might be a problem with the construction of this problem. Yep, so there's a slight problem here. Yep, so this is actually an impossible situation. Because we would need what? Minus 31, so there would have to be like negative 11 elements in C. But if I'd constructed the problem correctly, then that wouldn't be an issue. Yeah, so this is just impossible. Okay. Well, anyway, oops. Okay, so I don't know what I want to say about this thing. I wrote this down. Here's the generalized inclusion-exclusion principle. There it is. So the way to think about it is that whenever you're unioning n sets, what you're really doing is you're adding up all the singles, add the singles, subtract the doubles, add the triples, and then subtract the quadruples. And so on in that fashion until you get tired of doing it or until you run out of sets. So that's kind of the answer to this thing. That's what this actually means, right? This is saying alternate adding and subtracting. And if you notice here, this is saying take k out of the n sets. And then here is a k-sized intersection. And whether or not you add k-sized intersections or subtract k-sized intersections is equivalent to this minus 1 to the k plus 1 feature. So anyway, that's the inclusion-exclusion formula in general. But for now, just stick with the single and double union things. So I just wanted to point out that this exists. It exists for all sizes of sets. There's not really any restriction. Okay. This is, I think maybe we'll make the determination this is not testable. Yeah, I didn't want to worry you guys too much. All right. So let's do one last thing today. So let's start with this example here. How many integer solutions are there to this formula? And don't worry about this theorem up here yet. We'll talk about it in just a second. But think about it. Yeah, this is finally stars and bars done right. So the point is that actually we can count the number of solutions to this equation without any combinatorial. Yes, 17. Excellent, excellent. So, okay. But the point is, we can count the number of solutions because we can do this in this way. We can say, well, I know for a fact that if this equation is true, then x2 is really just equal to 17 minus x1. So here's my question for you. If I choose x1, do you really have any choice? And the answer is, well, not really. Not really, no. So that's good, right? So we can actually count up the number of solutions. So in this case, the number of solutions to this equation are going to be, well, you can either pick x equals 0, x1 equals 0, in which case x2 is going to be equal to 17, or x1 is equal to 1, or it's equal to 2, all the way up to 17. So we have to ask ourselves, how many solutions is this from 0 to 17? Well, we see that there are 18 possible solutions. So what do we make of that? All right, now let's pay attention to this theorem. Does it match with this combinatorial gibberish? Well, let's check. So m is the number of variables. So there's m equals 2 variables here. And n is equal to 17. Therefore, of course, you can say, well, this is an example, not a proof. Fine. There are 17 plus 2 minus 1. Choose, and then either you can choose m minus 1, so m minus 1 is 1, or you can choose n, which would be 17. So, yeah, m is the number of variables. So as it turns out, this is 18 choose 1. Whoops, not 81, 18. So you ask yourself, well, how many ways can I pick out of a bag of 18 things? How many ways can I pick one of those things? The answer is 18. Now, you can also say things like, oh, I can evaluate the factorials. 18 factorial over 1 factorial, 17 factorial, and do all the cancellation. And then this is just 1, and then this is just 18. So it matches, at least in this case. Okay. So let's look at another equation. What about this one? How many integer solutions are there to this thing? Well, unfortunately, this is not as easy, right? And so, basically, the reason why this is called stars and bars is because what you do is you draw out, in this case, you would draw out 34 slots. And then what you would do is you would pick 2 of those slots. Let's just pretend that. So we pick this one and put a bar in it. We put this one and put a bar in it. And then the rest of them has stars. It's actually easier to draw this type of star. Okay. And so the question is, why is the number of ways to place the 2 bars amongst 34 slots the same as the number of solutions, integer solutions to this equation? And the answer is, well, there are 3 variables. So we make 2 bars. So what's the deal with that? The deal with that is that here, you would add up the number of stars and you would get 2 is assigned to be x1. And then here, because the last 2 are separated, so we get 2 is equal to x3. And here, I guess we would get what? 28 is equal to x2. Yeah, the 2 bars are based off of the 3 variables. 2 bars. So when you think about it this way, the 2 bars are the number of ways that we have to divide. Yes, exactly. You need 3 groups. Therefore, you have to divide them with 2 bars. And that's where the -1 comes in the formula too. So, and as it turns out, the number of ways to pick the positions of these 2 bars is, in this case, 32 plus 3 minus 1, right? Because this is the number of bars. Choose 2 positions, which is also the number of bars. Yeah, when you add up the number of stars, that's what each variable is equal to. So for instance, there's 2 stars here, so the x1 is 2. There's 28 stars here because I just drew a bunch of dots. So there's x2 is 28, and then I drew 2 stars at the end, but it can be any number, right? We could have, if I had drawn more stars, we could have shifted the bars around and gotten any combination such that, and notice here, the rule is that all the numbers of stars have to be bigger than or equal to 0. That's what prevents us from having infinitely many solutions, right? If you could have, say, negative 17 as x1, then you could have x2 as 17 and then x3 as 32. And so you would see that there's infinitely many solutions because you could just always pick minus x plus x plus 32, and that would get you to the answer. The problem with that is that there's infinitely many of these. So let's at least calculate this number. So this is 34 choose 2, which is equal to 34 factorial over 2 factorial, 32 factorial, which when you do a little bit of simplifying is going to be equal to 34 times 33 over 2. I'm seeing 561. So this is a pretty cool method, actually, to solve these types of equations. And now you kind of see why it's called stars and bars. That's why I was so unable to answer that question in the last class, is because I realized halfway through that the method of solution was this. And clearly I couldn't get to it in time. I was like, oh, there's too much new stuff. I can't teach all of it. So let's do, we have 3 minutes. Let's do one more problem. So how do we do this problem? Whoops. First, let's not cross that out. How do we do this problem? Better. So we do this problem by basically doing the same thing, except you notice that x1 has to be bigger than or equal to 3 in this case. x2 has to be bigger than or equal to 4, and x3 has to be bigger than or equal to 2. So basically all of them have lower bounds now. And if they all have lower bounds, then what we know is that we can actually define a new variable. So the trick to this is define new variables. And the new variable is going to be y1 is equal to x1 minus 3. Y2 is going to be x2 minus 4. And y3 is going to be x3 minus 2. So the thing that we realize about these variables is that now yi is bigger than or equal to 0, right? So now 0 is bigger than or equal to y1, 0 is bigger than or equal to y2, and 0 is bigger than or equal to y3. So this gets us most of the way. Yeah, so actually you can do that too. I think, so yeah, basically what we can do, you're almost right. So what we get to do here is, actually what I'm going to do is shift the variables over to the other side. So I'm going to say y1 plus 3 is equal to x1. And then we're just about to substitute. So then we say y2 plus 4 is equal to x2. And we're going to say y3 plus 2 is equal to x3. And then, yes, you substitute everything in. So you go y1 plus 3 plus y2 plus 4 plus y3 plus 2 is equal to 32. So then what we do is we collapse all these terms and subtract. So we basically subtract off a 2, a 4, and the 3. Yeah, exactly. So you subtract, and then what you end up with is now you end up with y1 plus y2 plus y3 is equal to, I guess what, 23, right? So at this point, we can calculate the answer in the same way that we did before, except now instead of 32, it's 23 plus 3 variables minus 1 for the bars, choose 2, which is the 3 minus 1. So cool. This is what, 24, 25, 25, choose 2. So 25, choose 2 is 25 times 24 over 2. So, which is actually just equal to 300, a nice round number. So the minus 1 comes in because if you remember when we were choosing all the places, so if you have a bunch of different places and you want to make this into 3 groups, right? 3 groups only requires 2 bars to do that. So for instance, if I put a bar here and I put a bar here, now I have, I mean, this is not 23, obviously, but this is 3 groups of all the slots. So this would set the third variable to 3, this would set the second variable to 1, and this would set the first variable to 4. And so I guess this, if the number was 8, this would work. So, yeah, so basically the point is that when you want to split something into 3 groups, you need 2 bars. If you want to split something into 5 groups, you need 4 bars because, all right. I think that's getting close to it for the day. Will I be on Discord after class? Not directly after class. I'll probably maybe be on a little later. I'm going to take a break for dinner. All right. Well, this lecture was definitely more comprehensible than the last. I'm going to tell myself that. All right. Have a good evening, people. Yep. All right. Not sure yet. Don't know what's for dinner. So, see you guys. About to go find out.